First of all, we have Dr. Zhen, assistant professor in the Department of Biomedical Engineering at Michigan State University. Welcome, Zhen.
Yeah, thank you so much, Paula. Hi, everyone. So I'm gonna introduce my research for the miniaturized microendoscope for the molecular imaging. And in the original title, I noticed that you're saying I'm doing the light sheet for breast cancer, organoid, and spheroid. Actually, I'm doing that, but just like today, I'm going to present the one we already finished, and we are trying the supercontinuum laser for this light sheet microscope, but the content will cover many about the miniaturized confocal, and I'll explain why we're working on this and link to the light sheet we're working on, and this is my research in the Michigan State University, and it's about the miniaturized microendoscope for clinical application and also the small animal preclinical imaging for the molecular imaging applications. And it's based on the MEMS scanner and actuators. So first I will introduce the MEMS-based confocal. It's a fluorescent microscope for cross-sectional imaging with a molecular level cell resolution with the help of the peptide and other small molecular, which is specifically targeting the tumor and cancers. And second, I'll introduce the in vivo imaging on the human gut in imaging in the GI tract using the MEMS-based microendoscope, which is the translational bioptics. And the third one, I'll mention a little bit about the two-photon, multi-photon, second harmonic imaging we're working on. And the unmet needs in the clinics is most of the cancer, especially the whole organ, for example, the colon cancer, and including the breast cancer, the tumor started in the epithelial layer, and for example, it typically in the colorectal cancer, which is deep in the around 500 to 600 in the human, starting there, and then it developed to the upper. So that's why it's important to see deeper imaging using the fluorescence targeting imaging modality to show the specific binding to the tumor area and with a very good contrast between the tumor and the normal area. And we're developing the multicolor infrared MEMS-based confocal fluorescent microscope with a MEMS scanner. And I'm gonna introduce the architecture of the confocal. It's quite similar to the architecture widely used in the light sheet right now. And we started this MEMS-based endoscope with this kind of architecture is cross-sectional imaging. For illumination, we use one arm and then using another collection arm with the off axis, and then put the MEMS scanner in the middle, which is the post-objective scanning mechanism. So nowadays, people use this kind of architecture with 90-degree to perform the light sheet microscope imaging with the camera. And we're doing the same thing also based on the similar architecture. At the beginning, we try to miniaturize the system. We use a MEMS scanner, and then the collecting side is using PMT or single photon detectors. And the scanner we develop using the electrostatic. We're also working on other modality, for example, the thin film piezo and electrothermal scanners. And this one the beam can be pushed by the micro mirror into the tissue deeply based on the post objective, which is the scanner close to the specimen. And the commercial system, for example, Pentax or Cellvizio, they only work on the visible range. They're working towards the near-infrared. And right now, we already have the near-infrared 780, which is close to near-infrared, and 785, which is exactly in the near-infrared 1 region. We're also working on the near-infrared 2 region with the supercontinuum lasers. And later, I'll introduce why we need the supercontinuum instead of the traditional CW laser. And this is a basic simulation using ray tracing, and the scanner we developed in the micro fabrication foundry in Michigan, and we integrate into the handheld system for the miniaturized packaging. And here we can see the goblet cell on the mouse tissue and of the colon area, and then with the dysplasia, which is close to the tumor, not tumor yet, but it's early status dysplasia, which is in the APC CPC mouse model, and you can tell the difference between normal and the dysplasia area using the dye staining. And then this is a mouse model we used, APC CPC mouse, and you can tell the dysplasia area. We did the biopsy also to confirm it's a tumor area. And then this is a contrast agent we used, which is a molecular targeting the tumor area with a peptide. And using the traditional CW laser, we can see this contrast using the specific binding. For example, 670 labeled peptide targeting the tumor area. You can see very bright signal compared to the normal area with a very high contrast. But actually, there's one thing is missing, just like the dynamics of the peptide binding. So with the supercontinuum laser, we plan to study the dynamics binding using supercontinuum, which is pulse laser. And also we are developing the FLIN system based on this supercontinuum laser to study the dynamics of the molecular targeting. And this is the study using the handheld system for the mouse. We also have a endoscope system for the rat, which is a colorectal cancer rat model. And this is a merged imaging with two color, and you can tell the difference between the anatomic, which is showing the morphology change, and the molecular change using the peptide staining. And furthermore, we also developed the 2D imaging with a 2D scanner or even 3D scanning system. And this is the one we are developing the 2D scanner with the MEMS on the silicon wafers. Usually we develop on 6 or 4-inch silicon wafer with a high yield. So you can potentially miniaturize this for less than 5 millimeter at the distal end with this tiny chip. This is developed in Europe. We collaborate with Argonne National Lab in Chicago, but the fabrication was done in Europe, Switzerland. And we also demonstrate the capability of the 3D using Phantom with the beads, for example, the horizontal cross-sectioning and the vertical cross-sectioning, which is very normal in the 3D imaging characterization. And then we move on to the Z imaging along the Z depths of the tumor area. We can see the crypts, and this is a tumor area because it's widely distorted. And you can see the contrast in the normal area with the peptide is bonding very minimal binding. The tumor area is bound a lot, so that you can see very high contrast. And right now we're working on the supercontinuum when we received it last year. So we are working on the study the dynamics of this bonding process, which is very complicated. Using CW laser, you can never achieve this, but with the supercontinuum it's possible. We're working on this. So later in the future, we'll introduce more details how we use this and study this. And the in vivo study with the miniaturized system, we study the human sample into the human body in vivo, because we can miniaturize to 5 millimeter. So we study this in the Stanford on the clinical trial on human. We scan the ICG on the polyps, and then imaging with the endoscope, and using the mosaicing algorithm, so you can stitch all these small area field of view and to get a large field of view imaging. So here, this is the whole big picture when you scan in vivo in the human body with the MEMS scanner. And we also developed the XZ scanning, which the scanner can move in Z direction directly with this one show more than 500 micron. So that means you can directly scan the cross-sectioning in the Z direction, extra scan, which has never been done before in the commercial or even the traditional confocal microscope. But with the MEMS, everything is possible in the miniaturized system without the tuning the focus by the traditional focus tuning. So MEM scanner can directly push the beam into the tissue directly. And this is a human study using the near-infrared dye 785 nanometer CW laser. And then we're working on the Supercontinuum to get dynamics. For example, the fluorescent lifetime. We try to get the whole frame to study the lifetime for each pixel. So we already get some pictures. So since it's not published, we will show it next time when we publish it. And the third one I'm going to introduce is a multiphoton, which is based on the cyclone laser from the FYLA. And since we have a collaborator in Michigan State who work on the pulse laser for a long time, and he's kind of famous in the pulse shaping area. And we have the facility to study the second harmonic and also two photon on the oral cancer and also head and neck for clinical applications. So currently, we try to distinguish the normal area or and the tumor area using this two photon and second harmonic using multi-color imaging simultaneously. So this is oral tissue we got from the model, the small, not small animals, sorry, large animal, canine, a dog. So dog oral tissue is very close to the human, so you can tell this cancer area compared to the normal area. If we can using the multiphoton to imaging directly using the optical biopsy, so it will help a lot without the real tissue sectioning. So you can in vivo imaging the tumor area directly. So the normal area, so when we use the multiphoton tabletop system, so you can tell the morphology is close to the gold standard histology slice. And also this is a tumor area. This is a displacer area. And we use the stitching to get a larger frame. So this is a traditional one we're developing using the tabletop system based on the Nikon inverted microscope and using the formal femtosecond laser. But right now we are moving towards the FYLA laser, cyclone laser, and we also get another one for MIT, and we are doing the collaboration using this laser in MIT for different kind of applications. And this is a miniaturized system. We use a 3D printed holder to assemble the MEM scanner to get a miniaturized system. And we also have the handheld system that is used for clinical applications. For example, the head and neck or the oral. So you can see the nuclei in the tissue. So finally, I'd like to thank everyone and also introduce a little bit about our new institute located in Michigan State. It's an institute for quantitative health, science, and engineering building. And we're also recruiting researchers. So thank you so much.
Thank you so much, Ben. Does anyone have any questions?
I have a question for the previous speaker. This is Lawson Osfried from Maria National Lab.
Hi.
I was wondering what's the resolution, the vertical resolution, scan and resolution of your MEM, and what is the lifetime?
Okay, so the scanner right now, the resolution is based on the optical imaging system rather than the scanner itself. The scanner can travel the whole Z 500 micron, but you're talking about
talking about the mechanical resolution, not really optical resolution.
Okay, so this scanner, since we like to travel very largely, we use a resonance scanning. So we run it at the resonance.
Okay.
At the Z. We don't stop at here. So usually for colorectal cancer, for example, the pathology, usually they view the vertical cross-sectional imaging directly for the pathologist, for the HE staining. So that's why we developed this directly using the vertical cross-sectional imaging, the Z actual scan, instead of step by step moving.
Okay.
So you basically directly get the vertical. And also we take advantage of the resonance scanning mode for the Z. Otherwise, you cannot achieve 500 micron in such kind of tiny area. So especially for the electrostatic.
Thank you.
Yeah, welcome.
Any more questions?
Yes, there is a question from Rodrigo on this.
Rodrigo?
Thank you very much for such a nice presentation. I just wanted to know if within your confocal microscope, when you do the cross-sectional image, if there is any identification of automated identification of cells that you do, or you're just doing the imaging at the moment?
Okay, we are only focused on imaging at this moment. So imaging, fluorescent imaging.
Okay, thank you very much.
Yeah. But actually, in the future, we are working on the fluorescence lifetime, if it's possible. So we're testing. Actually, we are using the portable system to do the fluorescent lifetime right now, based on same architecture. It's not published yet, so we haven't showed the result. But we did get the result 1 month ago, before Christmas, using FYLA's laser, supercontinuum laser. The imaging looks very promising.
Yes. Okay. Thank you very
Yeah.
much.
Yeah.
Anyone else would like to ask something to Zhen? Yes, Shata.
Good afternoon. Thank you very much for the nice talk. I had just a question
you.
about the sensitivity of all this imaging technique to the noise of the source. You used quite a different number of light source, and the last one I think is a femtosecond laser, right? How sensitive is it to amplitude noise and also phase noise?
So we cover both confocal fluorescence and also the multiphoton. So you're mentioning the confocal or multiphoton?
Actually, both of them. If you
Okay.
can a general
So
answer.
for the first one, actually, is the signal to noise ratio is quite high because we are taking advantage of the molecular imaging using the peptide, which is conjugated with near-infrared dye. So then all you see is the fluorescence imaging. So that's why you get a minimal, when you say noise, for example, using the reflective confocal, you will see speckle, but this is not reflective confocal, it's fluorescent confocal. So the signal from the dye itself is very bright. And the second one, the multiphoton, if you're using second harmonic, yes, the signal to noise ratio will drop a lot because it's the second harmonic. It's a kind of it's not, you are not relying the dye itself. It's relying the autofluorescence from the tissue. So and also case by case depends on what kind of tissue you're imaging. For example, if you're using imaging the collagen in the tail, that's very strong because the tail has a lot of collagen. But if you're imaging other, say for example NADH or FAD, that will be quite low. The signal to noise ratio will be low. But you can lower the scanning speed, say pixel by pixel, and integration time longer. So you potentially can increase the signal to noise ratio.
Makes sense. Thank you very much.
Yeah.
Thank you very much, Zhen.
Okay,
Again.
thank you.
Finally, we have Dr. Maria Perez. She's postdoctoral researcher at the Photonic Nanosystems Group in the University of Freiburg, and she will talk about the use of lasers for signal molecule spectroscopy. Sorry. Welcome, Maria.
Hello, yeah, can you hear me well?
Yes, we can hear you perfectly.
Okay, so yeah, as you said, I come from the University of Freiburg in Switzerland. I work in the Photonic Nanosystems group led by Professor Acuna. And yeah, so we do single molecule spectroscopy in our lab, and I'm going to show a bit what we are doing with supercontinuum lasers. So a bit of an overview of what we do in the group. So as I say, we do single molecule spectroscopy. So we look at the fluorescence from individual molecules to understand how light interacts with them on the individual level. And for this, we use DNA nanotechnology. So we use DNA as a breadboard to manipulate fluorophores and to combine them with metallic and semiconducting particles that I'm showing in this sketch to study their interaction in different properties and to study basically plasmonic and nanophotonic effects. And another thing that we do in the group is super resolution microscopy. So basically fluorescence microscopy beyond the diffraction limit. And for this, we also use DNA nanotechnology. And here I'm just showing some examples of these super resolution images. So why is a supercontinuum laser useful in this topic? First, if we want to study the interaction between fluorophores and nanoparticles, we are limited to the sizes and shapes of nanoparticles that we can use. So we have a defined resonance wavelength that we have to adjust to. So since we are constrained on that side, then it's ideal for us to have a source that can be a laser source that can be tunable so that we can adjust our excitation and our fluorophores to the resonance of the nanoparticles that we are using in every particular case. And also if we want to do multicolor experiments, instead of having multiple laser lines, we could have a single laser source that we can, from which we can extract different laser lines. I will show later how we do this. Another thing that is important for us, because we do a lot of fluorescence lifetime imaging, since this is a good parameter to study the interaction between metallic nanoparticles and fluorophores. And this, for this, it is good to have a source that has a short pulse duration, like the ice blink. Is the laser that we have in our lab. It has a short pulse duration of in the order of picoseconds, and it's good because usually fluorescence lifetimes are in the order of nanoseconds, so we can clearly see, so we can measure this lifetime with good resolution. Second, also this laser has the appropriate power for confocal single molecule measurements, which is what we normally use. And this power is stable over time, which is important for us because we acquire lots of statistics. So we do experiments over long periods of time, and we need to be able to compare them without having oscillations in power. So here I'm showing a bit how we incorporate this supercontinuum laser in our microscope. So we have a confocal microscope that is home built. So this is the body of the microscope. This is the same image looking from the front and the back of the microscope. So here is our supercontinuum laser. And what we do is take the fiber. The first element that we have here is a wheel in which we have clean-up filters, so filters to select individual laser lines. And it's a wheel that we can rotate via software just to select individual wavelengths. And in case it's not here in this picture, but we also have an AUTF, an acousto-optic tunable filter that we can also use to select individual laser lines. Up to 4 channels at the time, and one can also use this to interleave them. So one can do multicolor imaging or interleaved imaging, changing the wavelength. Then we have some mirrors for optical alignment, a telescope to expand the size of the laser beam to fill the back focal plane aperture of our objective. We have some neutral density filters to adjust the power, some components to control the polarization of the sample plane, and that's it. And the rest is just regular confocal. And just to mention what we use the supercontinuum laser in our lab. So initially we had several lasers to do these experiments, as I was saying, to adjust the laser wavelength depending on the structure that we were looking at. But we have shifted. Now, instead of using individual laser lines, we just use the supercontinuum laser and playing with the acousto-optic tunable filter or with the cleanup filters. We select individual wavelengths depending on the application. We have already some publications using this laser. So I show here an example in which we have gold nanorods that we assemble together using DNA nanotechnology, as I was saying. Basically, based on the size of the particles that we have and the geometrical constraints imposed by our DNA breadboard, we run some simulations to see. So in our case, we wanted to optimize this parameter, the directivity. So we ran some simulations to see what was the effect of this parameter over the wavelength. And we find that we expect this directivity to be maximum in this wavelength. So then, as I was saying, this is a constraint. So we have to adjust to this. So since we know the maximum wavelength we expect, we chose a dye that would be overlapping with this. And then we need to select our excitation wavelengths to excite this fluorophore as optimally as possible. And for this, we use the supercontinuum and just with a cleanup filter, select the right wavelengths for optimal excitation. And yeah, indeed, we showed that this was working. So yeah, this is the advantage of having a supercontinuum laser, that you can adjust the wavelength to basically any experiments that you're running. So yeah, now we use it daily in our lab for most experiments. For multicolor measurements, for plasmonic measurements, especially for lifetime imaging, as I was saying. And this is just a summary of what we do. So thank you for your attention.
Thank you very much, Maria. As before, if anyone have any questions, please ask Maria now. It is the moment.
Thank you very much for the nice presentation. It's just a quick question regarding your setup. What you mentioned is the high versatility of the laser, which is clear. What I was wondering, you are using this acousto-optical tunable filter.
Mhm.
And I was wondering what is the bandwidth that you can select and the wavelength range where you can tune your laser, because I guess it's the spectral output of the laser would be larger than the specifications of your filter. So how do you manage this?
Yeah, so with an AOTF, you get something that is quite sharp. I don't know, like 5 nanometers, the bandwidth, but then you can get some like second harmonic going through. So we combine both things. We have cleanup filters and AOTF. So with the cleanup filter, you make sure that you don't have spurious wavelengths. And with the AOTF, then you can do this multiplexing, interleaving different wavelengths. Yeah. So it's a combination of both things.
Okay. Thank you very much. Thank you for the nice presentation.
Anyone would like to ask something to Maria?
Yes, I just want, thank you for the presentation, Maria, by the way. I would like just to ask you, how do you synchronize the laser with the detection in case of film? Because you mentioned you are also doing film with this setup.
Yeah, so
maybe it's a question also for the manufacturer, but how do you synchronize the time pulse with the detection?
So, yeah, the laser has an output to which you can connect that delivers you a TTL signal, and then we use this to connect it to our detectors.
So you have a TTL external lookup. Okay,
yeah.
Thank you very much.
Thank you very much for your presentations. They have been really interesting. And I would like to thank all the attendees today and your participations. So thank you very much and have a nice morning and afternoon, depends on where are you. And you can find this video on the YouTube and also in LinkedIn tomorrow. Tomorrow you can find them. Okay? So thank you. Thank you very much.